So I have erased all of the other stuff here. I've left the equation in terms of x, and I've added the word damped. This is a damped harmonic oscillator. It's also forced with this term here. So we're going to use the trick in section 3.6 is instead of looking for a solution x, the real part will actually add this unnecessary y, and we'll work in terms of the complex variable z. So z is x plus iy, and z double dot plus 2 zeta omega times z dot plus omega squared z is going to be little f times e to the I capital omega t. So the forcing is now complex, and the solution is now complex. But because this is a linear differential equation, we'll be able to solve it and then take the real part at the end, and it's going to turn out to be easier. So what we're going to do is we will try a solution z is equal to some amplitude times e to the I omega t, where this omega is exactly the same as this one. And that's because if you force something to oscillate at a certain speed, no matter what the natural frequency is, eventually the system will go with the thing that you're forcing it at. And the terms acting according to the natural frequency will damp out because of this damping. And all that will be left is the steady state behavior. And so that's what we're looking for here, is the steady state behavior. We're going to ignore transients on this. So we're just going to try this thing. Well, we substitute it into this equation, and you see what we get. So z dot then will be I omega a e to the I omega t, and z double dot will be minus omega squared a e I omega t. And so the z double dot, we wind up with minus omega squared a e to the I omega t plus 2 zeta little omega times I capital omega a e to the I omega t plus little omega squared a e to the I capital omega t, and that has to equal f e to the I omega t. If I factor out the a and I factor out the I omega t, we get a, on this side, I'll leave that there for the moment, minus omega squared from this first term plus 2 zeta omega I from this term, omega, plus little omega squared e to the I omega t. So that should get everything, and that's supposed to be equal to f e to the I omega t. This thing is constant. This is constant. This is the oscillator, the e to the I omega t, so this times this must equal little f. So therefore, the resulting amplitude, the complex amplitude, will be little f divided by all of this thing. Little omega squared minus big omega squared, that's this one minus this one, plus 2 zeta little omega I big omega. Well, we started with a real big F, and there's therefore a real little f. So this is real. The natural frequency is real. The forcing frequency is real. The damping is real. Okay, the only imaginary part is there. So if we multiply top and bottom by the conjugate of this thing, we get f times omega squared minus omega squared minus 2 zeta omega I omega. And then on the bottom, we have omega squared minus big omega squared all squared plus 4 zeta squared little omega squared big omega squared. And now we're in a position to say what the real part of our solution is. We can now say what the real part of A times e to the I omega t is, because we have the real and imaginary part of this in a separable kind of way. And we have, so that this number is complex and this number is complex, we can multiply the two together and take the real part. And in essence, what's going to happen is we're going to be able to account for these things as a phase difference. But the key point is that the solution process was very straightforward. Once we plug in e to the I omega t in this thing, the rest is just straightforward algebra.